Did it. Okay, go ahead.
Got it.
Hi, everybody. Welcome back to VTSS. And today we have Eric Eisenstat, who's going to present on singular vector regressions. And let me also thank Peter for joining us for the chat on the paper. The rules of the game are the usual. We've got 60 minutes. Feel free to ask questions in the meantime. Then we're going to stop the recording. And then we just open for an informal discussion. Sorry about this. We have a minor technical difficulty today. There was a problem in sharing the slides from the Eric side. So I've got the slides on my side, and Eric, whatever, I don't know, just you nod on one side or whatever. We'll figure it out, and I'll, that's it. So I think off we go, and that's it.
Okay, great. Well, thank you very much, Michele, and everyone. It's very nice to be able to present a lot of people across the globe at different time zones. So this is a paper with Rodney Strawn. I guess next. Yeah, there you go. A little bit of a delay. So the basic idea is that we're looking at is this throughout in the literature in the last couple of decades, the use of time series econometric models for structural inference, like getting the dynamic responses of economic variables to various shocks. And what's been essentially documented is a bit of a disconnect between what we use as econometric models and what we try to match to in terms of the economic models and what the implications of these disconnects are. So we summarized this and outlined the common strategies that have been applied. This has to do with things like various issues like non-fundamentalness, excess shocks, and things that occur that have been documented in the literature. And from all this, we derive a new representation that we feel resolves some of these issues, at least in a theoretical sense. So that's the basic idea. So to motivate this discussion, we'll go through the simplest example we could think of. This is taken from a paper by Eric Leeper and co-authors, fairly well-known paper in Econometrica from 2013. And so what they present there is a very simple theoretical model with fiscal foresight. So the basic components, we have an exogenous tax rate process. The key thing is that the tax rate, so if I move my mouse, can you see that? No, it's okay. So we got this, maybe I can do this. Okay. Yeah, so we got a tax rate process. The key thing here is that the tax rate at time t is determined by a shock that occurs with a lag. So there's an implementation lag. So the shock occurs at time t minus q. Q is the implementation lag, and generally non-zero. We have an exogenous technology process, very simple, and endogenous capital. And so this is, very simple thing to solve. Solve for the equilibrium, log linearize it, and what you obtain is this capital accumulation equation for the log capital deviations from the steady state that are functions of the tax rates, expectations of tax rates. And the key thing is that what it becomes a function of our future tax rates, and subject to these parameters, where one of the key parameters in this again theoretical development is this theta, which is in theory restricted to be between 0 and 1. So that's just the basic setup. So next, from this, again, take the simplest case. We assume that the implementation lag is 2. So let's say there's a tax announcement, and then 2 quarters later, it gets implemented. So that it gets reflected in tax rate after a 2-quarter delay. Then we can derive a very simple state space representation for the 3 states in this model. The 3 states are capital, technology, and taxes, again, in deviations from the steady states. So this is a 3-dimensional vector called y tilde time t. We put all these things together, and what we get in this linearized state space form looks like a Varma 1-2 process. So we've got the autoregressive matrix on the left side with the 1 minus alpha L and so on. And the important part is the polynomial matrix on the right-hand side, the theta tilde L, which would look like this in this form. And one of the key things is that it's a 3x2 matrix. So again, this describes our states process that we derived from theory. And the key features are that there are 3 states, but only 2 shocks. The 2 shocks are the technology shock and the tax shock. The tax shock is getting implemented with a lag. So when we get to this phase, again, we look at features of these polynomial matrices. One of the important features is where the zeros of this moving average polynomial, the theta L matrix, lie. So we can easily solve it in this case if Z, some complex value Z, is a value where the rank of the matrix is less than 2, so it loses rank. Then all the submatrices, 2x2 submatrices, must have determinant 0. So it's very easy to show that obviously this leads to this. The only possible Z are those that solve these 2 equations, theta plus Z0 and theta squared 0. So the only solution that could ever occur is in the very special case when the parameter theta is exactly equal to 0. In all other cases, this polynomial moving average matrix does not have any zeros. So it's determined as 2 for any value of Z, as long as theta is not equal to 0. And that leads to this interesting results on the next page. Next slide, is that we can always find a matrix theta LZ. We'll call it a left inverse. Here's an example. It's actually not unique, but this is the simplest possible form. And you can easily show that there exists this matrix that if we multiply the theta tilde LZ on the left side by theta Z, we get this, essentially is like a tall identity matrix, so identity with zeros. So in other words, what we can do is we can left multiply by this theta LZ to get rid of this moving average terms in this Varma 1-2 representation, right? And again, the key features here to notice is that all the entries in this theta LZ matrix are polynomials with a finite degree. And in fact, it is exactly, the maximum degree is exactly 2, which is by no coincidence equivalent to the assumed implementation lag. So assume that implementation lag, that's the maximum degree of the theta Z polynomial matrix. We can essentially invert it in this case and obtain with this finite order polynomials that go into this theta L matrix. And what all that leads to is that our Varma 1-2 representation in this case has an equivalent VAR3 representation. So on the next slide, looks exactly like this, right? So this is all straightforward derivations. In other words, in this particular case, we get a finite order VR representation exactly. So these will have the pi now tilde matrix is just the standard autoregressive 3x3 matrix, and all the entries are polynomials. All their degrees are less than or equal to 3. So it's a finite order VR representation. And again, the reason we're getting this is because we've got the number of states, in this case 3, exceeding the number of shocks 2. So this is not a standard representation that we usually see with the VAR because there are more variables than shocks. So we refer to this as a singular VR, and we'll see that it's got actually, because of this, it's got advantages from a theoretical point of view, but also some difficulties from a practical point of view. So next. Now, if we work our way backwards, we see that the implied spectral density for this states process, which we can again easily derive, is necessarily singular, right? So if we work out the spectral density, it's easy to see that this spectral density, first of all the entries are rational, so it's a rational spectral density, but it's also singular. It's a 3x3 matrix, but its rank is going to be 2 for any given value complex number set that you plug in there. So in general, this would be a general feature. The normal rank of the spectral density matrix associated with this process is going to be precisely the number of shocks in this case, which is going to play an important role, right? So this means that, back to start. The rank of a spectral density matrix can be related to the number of structural shocks in this derived theoretical process. So next. Now the question is here, okay, that's on the theoretical side. Let's say we want to do something like estimate the dynamic effects of a tax shock on capital, so the response of capital to tax shock. How do we do that? Well, we go out, we collect some data. Let's say we have n variables that we can observe, and we'll, summarize what we typically do is we would assume some data generating process now for the observed process YT under some conditions, stationarity. Would assume it's got a spectral density, and then essentially we try to match the two. The econometric model that we've specified for this observed process to the theoretical model that we've described, let's say, so far. So we specify an econometric model. In practice, it's usually, let's say, vector autoregression or a VARMA more generally, or it could be a dynamic factor model and so on. This is things where we can estimate the things like the parameters from and so on. And then try to match it to the states process that we get from these theoretical models. And by this match, we're then would argue for the use of certain restrictions that would be consistent with theory to then identify the shocks or identify more generally the impulse responses, forecast their variance decompositions and so on. But in practice, we almost always have like a mismatch, because when we specify a VAR, let's say, or a VARMA or a DFM, underlying this modeling approach is almost always an assumption that the spectral density of that observed process is full rank. So if we've got n variables, the spectral density of the sigma y, the rank is going to be n. But we've said that in the process we derived for the states from the theoretical model, the spectral density is singular. So we've got a mismatch. We're working, on the empirical side with the model, it's got a full rank spectral density, but we're trying to match it to a theoretical process that's got a singular spectral density. So, and a lot of the sort of issues that arise, argue, come from that mismatch. So I'll go to the next slide. What kind of happens in practice is we, in a way, try to reconcile this mismatch. And there are a number of ways that have been that this has been done. So the most common way is to say, okay, let's try to get from our states process, derive a process that has a full rank spectral density that's not singular. So the most common way that this has been justified is to say, okay, we've got this process with 3 states and 2 shocks, but we can take a sub-process. So we choose, 2 of the 3 states to match to 2, let's say, observables. So if we take 2 of the 3 states, we can obtain a subsystem, again, just straight derivations, which is a square system. It's got 2 states and 2 shocks. And that turns out to be a VARMA 1-1. Now, the key feature of this VARMA 1-1 in this case is that this polynomial matrix theta, the 2x2 polynomial matrix theta, now will have zeros. And in fact, easy to show that the determinant of it has exactly a 0 that's equivalent to theta. But by assumption, theta is between 0 and 1. So this polynomial moving average matrix does not have a left inverse. It doesn't have a finite order polynomial that can be pre-multiplied to obtain a left inverse. This is what is typically described as a non-fundamental VARMA system. So we cannot invert it to obtain a finite order vector autoregression. And in fact, in this case, there is no way to even approximate it with a finite order VR, there's not even an infinite order VR representation that would exist. This is sort of the key point made by Leaper in their paper. Now, it doesn't really matter that you choose capital and technology here. If you choose capital and taxes or technology and taxes, you get exactly the same result. So you pick any two states from this, you derive a square system, it's not going to be invertible. So there won't be any finite order VR approximation that could possibly exist in practice, right? Yeah, so we'll go to the next slide.
Can I say something?
Yeah.
So once upon a time, I was a macroeconomist who believed all this stuff macroeconomists do, but now I'm more of a statistician and more skeptical. So I think more like a statistician. What is the data saying? Okay, so in terms of that Leaper model, as long as the MA roots are not on the unit circle, you always have an invertible and non-invertible representation. So they're observationally equivalent, right? Now, if you're Leaper or whoever macroeconomist, and you cling to that model as that's reasonable and that's got to be the truth. Okay, fine. Then I agree with you. Then that's the way it is. Too bad. But if you look at it like a statistician, then you can there's an observationally equivalent moving average term that's invertible as long as the roots are on the unit circle. Anyway.
Yes, no, I agree with you.
I've sort of revealed some of what I think in advance. Anyway, that's all.
I think it's a valid point because, in fact, if I want to forecast capital and technology, none of this is really an issue because yes, I can obtain a VR representation by flipping the roots, and then I can forecast. The issue here is that you want to get responses to these structural shocks. So right, so if you want to write it down as the structural shocks as a linear function of the observed capital and technology, yes, I agree. You can invert it, but then you would have to write it down as a function of future observations of capital and technology. Right? You can write down the structural shocks as a linear function of present and past capital and technology. So it wouldn't be standard VR.
Okay, I haven't thought of that, but I won't deny it. One other small technical point I'd like to make. You talk about shocks and states, and then you have variables. Now, part of my problem is I think my eyes are faltering, so I'm more listening to you than looking at the screen, and that way I can understand better. But for example, I'm looking at your page 9 now, and you've got Y. Usually Y means the vector of observed variables, but maybe you mean the vector. Now, something you're not mentioning, but there's sort of three things going on in these state representations. You have the data, or what the engineers call outputs. And you have what economists call shocks, or engineers call them inputs. And then in the middle of all this, in the transfer function, you have the states, which are in principle unobserved, unless they're observed through the outputs. And there you have this observability condition and so on. So I haven't heard you make that. Now, maybe it doesn't matter because you're just giving a motivating example. But anyway, that just arose in my mind as when you're talking about the number of this is smaller than the number of that, you can have many more states than observations, as you presumably do in a dynamic system. Okay, I just wanted
I think I'll skip in a few details in the notation. So if you write down in space-based form, we think of it as we've got the states, and then we assume that two of the three states are perfectly observed. So without a observation equation that observe KT and AT is like a identity in the 0 times the states. But I think in the more general case, we'll write it out more explicitly. But so in this case, we're just kind of when I say YT, I mean the observed some observed capital and observations on capital and technology being matched perfectly to two of the states.
Okay, so in this case, observation vector equals state vector.
The
No,
sub.
not quite.
Sub
No, there's a third one there. Okay, anyway, go on.
Yeah.
Let's not get
I
lost.
think maybe a bit, general. So again, it's about this hypothetical matching. Right? We got observations, and then we define a process. We're trying to match it to a process that we hypothetically derive from some theoretical models. In this case, a very specific model, more generally a class of models. So if in this class of models, theoretically, this parameter theta is between 0 and 1, we get a non-fundamental varma, we cannot match it to, say, a VAR. This is pointed out by Leeper. I'm just sort of summarizing what's some of the issues that have been brought up in the literature. Then we can look at it, okay, say, well, that's just one type of model. Let's say, for whatever reason, we can set theta to be greater than 1. Then we don't have a non-fundamental varma. That is, we can write down the structural shocks as past and present and past combination of observed variables. But even in this case, the argument that we can approximate the varma with the finite order VAR, has been pointed out, could be shaky, because so we do like a little experiment and plug in 1.1 for theta and 0.1 for the steady state tax rate, and then calculate out all the VAR coefficients that we would get in this representation. We see that even at the 50th lag of this VAR representation, we still have like coefficients that are like 0.84. And so what that basically says is that if we want to approximate a varma 1,1 with just the pure VAR, in this case, we would need to specify at least 50 lags, right? So it has to be a really long VAR. And again, this is related to stuff in the literature with George Kapitanias and I think Don Poskin and others have done simulation experience and things, and have pointed out the fact that for certain DSG models, you would need like really large lags of VAR to approximate these implied varma processes that you get from the theoretical side. So that's all on that. Like, the issue that I wanted to point out is that in order for us to even try to match a two-dimensional system, we have to really make a stance on the fact that in theory there are only two structural shocks. And the question that doesn't really get asked is, like, how do we know that there are two structural shocks, and what are the implications if that's not correct, right? What exactly are we matching to when we specify a 2x2 system? So there's been a bit of work done on this as well. And so the example here would be, let's say that we don't assume that there are two shocks. Let's say we instead assume that there's only one shock. Well, if there's only one shock and we follow the same procedure, we extract one variable. Let's say it's capital. Well, we can write down an ARMA model for just for capital. In this ARMA model, we'd have a UT as the residual. From the theoretical side, we can also extract for the state capital now an ARMA process, and it's going to be an ARMA 1,1 process. So there's a match there. But the issue is that this residual UT that we would end up estimating in this approach is some linear combination of present and lags of the tax shock and the technology shock. So it's neither one or the other, right? We would estimate the residual UT, and again, we can forecast capital from this model, that's fine, but we cannot get the effect of a tax shock on capital from this univariate ARMA 1,1. So it's about trying to get the dynamic effects, or trying to, as I refer to, identify the shock from the data. In this case, if we specify the number of structural shocks, what we end up is with this issue that's some refer to non-recoverability. You can't recover the shocks, the structural shocks from the reduced form residuals. So we go to the next screen, because in essence, this is a more general issue. This refers to this sort of criticism of using small scale VAR models, that if you estimate like a three-dimensional VAR model, the best you can match to are three-dimensional theoretical models.
Can I say something here?
Yeah.
Basically, I would just say instead of non-recoverable, you don't need a new word. It's just identification. I think it's the same old.
Yes, I agree. But these are the terms that are being thrown around, right? So we've got non-fundamentalist, partial fundamentalist, recoverability, non-recoverability, excess shocks, deformation. There's like all these terms that are just flying around the literature trying to describe all these
actually, I agree.
mismatches.
Too much jargon and verbiage, which adds to confusion. But in the factor model literature, your epsilons or shocks or whatever you want to call them, these are in principle can be identified just from rank assumptions and basically just from you don't need so-called structural economic assumptions. Anyway, well, I understand what you're doing. You're following the kind of standard economic, macroeconomic reasoning where you go from theory to data, as opposed to the other way around. Like in the factor modeling, you go from data to model. Or I should say,
that's kind of what the proposal is, that we can start with the,
anyway,
the other way around.
The key issue is, well, I'm getting ahead of some remarks I wrote down. I'm supposed to say them at the end, but I think the key issue, one of the key issues is identification. Anyway, go ahead.
Yeah, okay. Okay, so this again, all this is about the various ways that have been approached in creating this match, and you're right. Like it's just generated all this different jargon, different issues that have been described in very different ways. So that was like sort of the most common thing, is that the issues with choosing a system that's too small and try to match that. So the other way, instead of choosing a subsystem, the alternative is to expand, essentially expand the system in terms of the number of shocks, right? So if we observe now, say, capital technology and the tax rate, instead of matching like just throwing away one variable and theoretically matching it to a subset, sub-process that we get from the theory, we say let's create again, a full rank spectral density by adding shocks. This is also something that's more or less explicitly been proposed and done in this macroeconometric literature. So in this case, what that would entail is to adding like one extra shock. So we call it at zeta t. This isn't coming from any theory, so there's no interpretation to it. We just need it to sort of complete the square, right? When we want all we're doing is forcing the number of states to match the number of shocks, so we can get a process that's got a full rank spectral densities that we try to match to the assumed Varma process or so that we're specifying for observed data. So what happens in this case if we try to do that is, now we get like a more explicit here. I can point out, it says here, underneath the equations, we got the yt is the observed, presumably observed vector. Y tilde t are the states that we get from the theory. So we essentially are assuming that the observed vector is the states plus some combination of present and past values of this shock zeta t, just some scalar white noise. Again, it's an ad hoc thing that gets added in just to make it square. So the question is precisely that, like, what exactly is it, right? And what are the implications of adding such a presumed noise? So a lot of times, literally, again, just the terminology, it gets called measurement error. So if it's measurement error, then what does that mean? Well, if measurement error, then it's presumably one of the states is getting measured with error and the other two states are perfectly observed. So we would set this third column that we've introduced in this moving average matrix, these theta 1, 3, theta 2, theta 3, 3. Two of them would set to 0. One of these polynomials would leave unrestricted. Again, as soon as we do that, all these same issues reappear. So if we go to the next slide, we see that we get so if we, like in this case, assume that it's just the tax rate that gets measured with error and the capital and technology get perfectly observed, then the determinant of this now polynomial moving average term will have a 0 at the point 0. So again, non-fundamental. And regardless of what we choose as the one measurement error, again, we can obtain all the same kind of results. So this non-fundamentalist issue that's been, again, talked about a lot, here in this case gets induced by introducing measurement error pretty much in the same way that it gets induced by eliminating certain states to create these square systems to match to the standard econometric models. Now, again, the more subtle issue here is, well, if we're going to introduce one measurement error, I mean, why wouldn't we introduce just all measurement error in every single one of these variables? So we assume that what we observe are the states measured with errors, so that there's more than one, that S is greater than one, right? The number of measurement errors is greater than one. Well, we will be obtaining in that case is that we have now 3 variables matched up to 3 states, but there are more than 3 altogether, more than 3 errors. So we got the structural shocks plus the measurement errors will be greater than 3. As soon as that happens, it turns out we cannot recover, in most reasonable cases, we cannot recover again any of the structural shocks. So we cannot identify the impulse response functions or the forecast set of variance decompositions to neither the tax shock nor the technology shock in this case. That it just, again, models everything out. Right, so we have to really, to work with the square system or to match it to a square system, take a really strong stance on how many structural shocks there are and how many measurement errors there are for this to kind of work. So we'll go to the next slide. And that's kind of the punchline. We can summarize all these various issues that have been proposed in the literature to the fact that we are forcing a square system out of what is naturally not a square system in theory. And what we need to do is take a really dogmatic stance on what the number of structural shocks are. And the key point is really here is that as soon as we impose this assumption that the spectral density has full rank, we kind of lose information on what the structural shocks, number of structural shocks could possibly be. So again, if we assume that there's some measurement error, but all we know is that our number of variables n, it has to be less than or equal to the total number of structural shocks plus measurement error. That's all. That's the best we can say. It's a censoring point in this case. Okay. So so all these. Anytime you specify like a square var, square varma, this is the issue we're facing. If we say we have a square var or a square varma with the full rank spectral density and the number of observations is n, we must assume really take a dogmatic stance that there are exactly n structural shocks basically. Otherwise, we run into all sorts of problems. So one way, theoretically attractive way around it is this generalized dynamic factor model that was proposed by Borneoliti and others over a series of papers, is one way to get around it. Now, a key assumption in that setting is that you need to have you need to assume an infinite number of variables to get any of these identification results. But what they do show is that under the assumption that you've got infinite number of variables, asymptotically, you can separate all the errors in the system into either common shocks, so intuitively, shocks that are pervasive in the system or significantly affecting most of the variables in the economy, and idiosyncratic shocks, those that are not pervasive, essentially. Now, these idiosyncratic shocks will include some structural shocks that are just not pervasive, like sectoral shocks, for example, and also any kind of measurement errors and ad hoc shocks that may exist in the matching, right? But what they show is that under this setting and under this assumption, you can get inference on the common shocks. So you've got something like, they focus on things like, the monetary policy shock, which would be presumably pervasive to the whole economy. So you can identify things like this, like monetary policy shocks, fiscal policy shock, and so on. Some sort of common macroeconomic shocks. You can get them out of this square system, even if there are more shocks than, in a very loose sense, it cannot be more shocks than variables because you have infinite number of variables that are being assumed. So it is like a theoretically attractive approach.
Can I just add something?
Yeah.
This is sort of stuff I'm doing now, and I've got a static version of it, but I've written out the dynamic but not typed it up. There's a way you can get calculate under Gaussian assumptions, calculate covariances of all these things you don't know in a model.
Yeah.
Factor loadings, all the covariances, all the I call them disturbances. You can call them shocks or
errors, residuals.
Anyway, you know, if you obviously you're not going to get n going to infinity, but if you know, and if it's decently large enough, you can calculate the covariances and between the two and the variances and all that. So you get some quantitative ideas of how well you're doing.
Yeah.
But anyway.
No, that is, I agree. So it doesn't like, you need, I mean, like in theory, n has to be infinite to get the identification result. In practice, you can get, I think you can gauge, how, I think you're right, how close you are to that, you know, limiting point.
I don't know what you mean by practical. When I think of
well, what we mean by practical, I'll get it. I guess I can just get a little more into it.
Let me just say the following: when I think of theory versus practice. Okay, when you do these dynamic factor models and people are, you know, ground away on the theory, trying to get consistency and this and that. Okay, obviously to get that, you know, for the math to work out, you've got to have number of periods and number of variables go to infinity. Okay, practical to me means it's like now there are, I don't know, thousands and thousands of these applications with people, you know, using this stuff for forecasting. I mean, they're just very applied people. I doubt if they know the theory. They're just taking it off the shelf. My idea of practical is, well, if it works and it gives you a decent result or maybe better than something else you've been doing, okay, it works.
Okay, I'll explain that part because it's important. So here practical means is the following. So if you want to apply the original GDFM, I mean, I think one of the original like actual empirical implementations was to estimate the spectral density non-parametrically, then factor it, and then obtain by essentially Fourier transforms the implied time domain representations. But one of the issues is that the time domain representation is two-sided. So the only thing that you could really identify are sort of things, time points in the middle of the series, issues like this. So in practice, like the actual implementation is quite difficult. The other big thing is that you need to estimate this number of common shocks. That's not easy either, and there are lots of consistency results about these estimating these common shocks. But when people went out and actually would try it in practice, you know, they would get these wildly different estimates depending on which test they use, like anything from like 1 to 10 or something. And there's no way to reconcile easily like all these different estimates. But it's a multi-stage approach. So in order for you to implement this non-parametric spectral density estimator and then decomposition and so on, you got a condition on the number of states, things like that. So the bottom line is there are not many papers that use directly this generalized dynamic factor model as it was specified. What usually ends up happening is you get some sort of restricted form, like you know, the dynamic factor model of used by Stock and Watson, right, or the Favart model. But these versions impose restrictions, and these restrictions that they impose actually sort of wipe out a lot of these theoretical advantages that this GDFM brings in terms of matching the empirical modeling to the implied theoretical process that you're trying to match to, basically. So that's what I mean by it's not very practical. Okay, so now with this in mind, I guess we get to the more general kind. This is all based on example. This is the general summary of it. So again, this is where we go from the data to the theory, right? So we'll observe any n-dimensional process, yt. We just assume that it's a mean zero and covariance stationary. Okay, so these can also be generalized, but you know, just to keep it simple. So, and the other assumption is that, okay, mean zero covariance stationary, we assume that it's got a spectral density is rational, and that the rank of the spectral density is some R that now can be less than or equal to the number of observed variables n almost everywhere. Okay, so we're just allowing it for it to be less than or equal to rather than strictly equal. And then so, yeah, there are a bunch of results in the control systems and engineering and stuff that show that you can factor such a spectral density into these spectral factors, call them B, Z, with lots of really nice properties. And one of the key things is that if we get that the rank of the spectral densities are strictly less than the number of observables n, then this spectral factor B Z is tall. So it's n by r, n is greater than r, strictly greater than r, and generically it will not have any zeros. So it will generically have a left inverse that we can pre-multiply. If, on the other hand, the spectral density has full rank, if r is exactly equal to n, then it'll have generically arbitrary zeros. And so it's, aside from very, very special cases, it will not have left inverse. It's just a simple observation. So that's the next slide. So from the full rank case, what we can obtain in the setting is that we can generally obtain a Varma, a finite order Varma representation. Yeah.
Just one clarification, if you don't mind, on the slide. Your first case, R less than n, means there are no zeros.
No zeros, generically, yeah.
Right, okay, I understand that. R equals n means there could be zeros. It doesn't
have to be zeros. Well, except for special cases, there will be zeros, right? The determinant will have zeros.
So there will be zeros.
Generically, aside from like, you know, measure zero subset of the parameter space kind of thing.
Generically means almost always.
Yes, almost always, exactly.
Okay, all right. I'm just trying to understand what that statement is.
So,
all right.
So Eric, you have about 16 minutes. So maybe we can leave the more detailed questions until the end.
Okay. Okay, so I'll run through this again, right? So we've got, because of these basic facts, what we derive as representations that we end up estimating is in the full rank case, we can get to a Varma process with finite orders for the autoregressive part and P, finite order for the moving average part Q. So these are polynomial matrices. They're square n by n and so on. Now, again, following from this, very straightforward, the determinant of the moving average part generically has zeros. So at best, we can order an approximated with a finite order representation, but we won't, there's no actual finite order VR representation that can be matched to it exactly. So we'd have to be, you know, again, really aware of how are we approximating it, or if that approximation even exists, because again, depending on where these zeros lie. In contrast, in the singular case, right, if we have that the rank is strictly less than n, what we obtain generically here is a singular VR representation with a finite lag order, which this is the pi L yt equal to r epsilon t equation on the bottom, right? So that arises naturally. There's no approximation involved. It doesn't matter where zeros lie and so on. Here, pi L is an n by n polynomial matrix. It's got a finite order. Every entry is a polynomial with an order that's less than or equal to p. And R is just the matrix of constants. It's n by r, and it's got full column rank R. Okay, so next. So then the question is, okay, what sort of theoretical models can we match that to, right? Because we've just derived, starting from a very general assumptions, representations that we can estimate. How do we match that to theoretical models? Well, on this side, again, going back to Leaper, what they actually end up showing is that a really, really large class of DSG models can be written in this form. So this is essentially a Varma 1Q. This includes things with foresight and so on and so on. But the other key feature that has been pointed out is the fact that when we write down log linearized solutions to DSG models, we get these Varma systems that are tall, that we get more states than the number of structural shocks, right? So again, that's a very general feature. And because of that, what we can always obtain, as discussed in almost every case, is a singular VAR representation that's going to have a finite order Q+1 for the states process, right? So now we've got sort of like at least a match in some general form. We've got a singular VAR that we've obtained just from the spectral density for the data. We've got a singular VAR that we've obtained from a log linearized representation of theoretical models. So we can go to the next step. And so now we can write down a general match. So YT is our vector of observed data. YT tilde is there are states we can obtain from some state space representations. This match where we have, even if we introduce things like white noise or any ad hoc shocks here in the vector S-dimensional vector set T, we can match YT to some subset of the states plus some linear combinations of these white noise. And so generally speaking, plug in our singular VR for the states representation. What we can do is write down our observed data vector YT in terms of the structural shocks, which are epsilon tilde T, and also these ad hoc white noise, measurement error, what have you, shocks, the zeta T, put them all together in this vector that's epsilon T. And the key point is that if we do that, again, if it turns out that the total number of shocks, S plus the number of structural shocks R tilde is less than N, then we still obtain a singular vector autoregression. So that's on the next page, the next slide. To summarize, it all depends on basically, the total number of errors that we obtain here. So R tilde, the number of structural shocks in theory, S number of measurement or ad hoc shocks. If it turns out that they're exactly equivalent to the number of observations, then we can match our data to the theory through some Varma PQ process, right? Again, in this case, we still don't get any finite order VARs. We can only get approximations, but in this case, we can match it to at least the Varma PQ process. What basically means practically is that if we estimate a Varma PQ process, the way we can get from that responses to structural shocks is to essentially assume that the total number of structural shocks plus any ad hoc shocks is exactly equal to the number of observables.
Can
on the other hand,
I interject quickly?
Yeah.
I think I'm starting to understand where you're getting to, because I didn't have time to read your paper carefully. I'll make more detailed comments about that. But I'm sort of getting the gut feeling now that your objective here is to try to identify the structural shock, which is the one with the economic meaning in practice.
Yeah.
But because YT, unless there's some sort of linear restrictions across variables, which basically never happens, because if that happens, you throw away the redundant ones. Basically, YT always has a positive definite covariance matrix, or at least its innovations do. So
covariance matrix, yes.
That's why you're adding this dimension S. Okay. So, okay, because I was worried from reading your paper. Wait a minute. How the heck are you going to account for all the variation of the data if you've got a rank deficiency? Okay, I think I'm understanding. You're throwing in these things you call measurement error. Now, but I'm wondering your next paragraph here. I know economists make S large so that inequality holds. My feeling is they're just kind of making things up, calling them sunspots and stuff. But to me, it sounds like, in terms of what you're doing, if you want to identify the epsilon, it's like pouring sand in your car instead of oil. It's just adding redundancy, and then you're making up restrictions to get rid of the redundancy. Anyway, I don't know if that's what you're doing, but I like that first paragraph here better. That's all I want to say now.
Okay, yeah. So basically, the only time, again, if we impose that we're working with Varma models that have a full rank spectral density, the only way, yes, we can identify structural shocks from estimating such a model is by assuming explicitly that the number of structural shocks plus the number of any ad hoc shocks is exactly N, right? It has to be exactly n. It cannot be greater than n, which we can, this is the part where we get really hard to justify. And this is where, we get into all these debates about, is a 3-variable VAR really enough to identify any structural shocks? I mean, the real question is, what sort of models could we possibly match a 3-variable VAR to? Well, only models that would have no more than 3 shocks, basically. If you've got any DSG model that has 10 shocks, you cannot get any structural shocks that would match up to that theory by estimating a 3-dimensional VAR. So that would be like motivation for estimating maybe really large Varma systems, but nobody does that in any case, right? This is just summarizing the facts. So again, if it happens to any model that leads to the number of structural shocks plus any ad hoc shocks that exceeds the number of observed variables, we cannot match anything like get any inference about the structural shocks in this setting, right? We cannot match that to anything we're estimating from the data. So the third case where we're again in, and I'll come back to your comment about linear restrictions, is that if it happens that the number of structural shocks plus these number of ad hoc shocks is strictly less than n, then again, what we get is an exact match in terms of singular VARs. So if we estimate a singular vector autoregression and we end up with a rank for the spectral density that's strictly less than n, what that gives us information about structural shocks. The first thing it tells us is that the number of structural shocks that we could match to cannot exceed that estimated rank, right? If we've got a rank estimate that's strictly less than n, we know that it's an upper bound on the number of structural shocks. So we know that we are matching to essentially all these DSG models that have these singular representations. So it's a very general sort of match, right? And the key point is that yes, you can estimate the rank of the spectral density from the data. That's we can identify that rank. And no, it doesn't have to be that they're exactly linear combinations in the same sense as in like standard factor models. It's more nuanced. Okay, so we'll go to the next slide. I'll go just briefly through it. The point is that when we allow for this singularity in the spectral density, again, we can derive a representation that better matches to the theory, but it's not as simple as saying now we just have a VAR that we can estimate using standard VAR methods. We've got new issues with identification. Again, we won't insist on that, that's in the paper. The key point is that the lag length in the system is not identified from the data. And because of that, the actual VAR coefficients in this pi L representation are also not identified. But the impulse response functions are unique, right? So if we're interested in the impulse response functions themselves, they are unique. We just have to deal with the fact that individual components like the lag length is not identified. Again, this comes from engineering and control systems. Okay, so next slide. So the bottom line is there are issues, like practical issues with this approach as well, but we think they can be solved essentially by parameterizing the lag length, the rank, and using Bayesian methods to shrink this lag length. The key thing, however, that we have to get around is the fact that in any situation where the spectral density rank R is strictly less than n, to use Bayesian methods, we've got to specify likelihood. In this case, again, standard approach of a density with respect to the Lebesgue measure doesn't work because it actually doesn't exist. It's not unique. So we need to use, in order to use likelihood methods in this case, we need an alternative approach. That's the key point. Okay, so I'll run, how much time? 5 minutes? Yeah, right, quickly through it. The way to get to it is, again, usual approach here, working with VARs is to write it down as a regression. So we could do the same thing. XT has the lags of YT, and R is just the matrix of constants. Again, the big difference here to a standard linear regression is that YT has dimension n, but epsilon t, the number of residuals here, has dimension r, which is presumably smaller. And because that dimension of residuals r is smaller, again, we cannot just obtain a regular density with respect to the Lebesgue measure to use as the likelihood. So what we need to do is essentially to reparameterize. We can do this without loss of generality to write down a system of equations. So once we reparameterize, we obtain the system of equations. We introduce this ZT. ZT has dimension r. We can now write down ZT as a linear regression for xt. This is just a standard linear regression. What we're essentially doing here is splitting the parameter space into orthogonal spaces. And it comes out really easy. So if we go to the next slide, this reparameterization, what it gives us is that essentially we have can view YT as a process defined on a R-dimensional submanifold, all very standard. It's linear, so very easy to work with. But essentially, the point of looking at it this way is then we can then use some concepts from differential geometry, where they just generalize the Lebesgue measure to this so-called Hausdorff measure. So loosely speaking, it's like a generalization of the Lebesgue measure in the Euclidean space to submanifolds.
Can I stop you just a tiny second?
Yeah.
This has to do with my comment.
Peter, let's just give him the last few minutes and then we can leave it for discussion. Is that okay for you, Peter?
Yeah, fine. You're in charge.
Just a minute. Eric, feel free to take a few more minutes, actually.
Okay, thanks. So again, they're very closely related. The Hausdorff measure, when r is equal to n, they're actually they essentially equivalent up to a constant multiple, the Hausdorff measure and the Lebesgue measure. So it's like a very natural generalization of the Lebesgue measure to submanifolds. And so in this case, basically what we can obtain is a density with respect to the Hausdorff measure. That's the equation on the bottom, which is the any density we derive for ZT, and then multiplied essentially with the hard restrictions. So go to the next slide. Again, the important thing is what we are left with is a restriction that must hold almost surely for any given, these are the linear restrictions that Peter was referring to, for any finite size t for the data. But here the point is that these linear restrictions are not just on the vector yt, they're on yt and lags of yt, so that they depend on the lag length p as well. So that's what makes it not quite that the natural thought is that, well, in practice, we're never going to have exact linear restrictions. Well, if we had like an infinite data set T, we might, detect that. But for a finite data set T, it really depends on the lag length, right? So we cannot say 100%, like it's not something that just gets violated with probability 1 in practice. There is a non-zero probability or possibility for to estimate a non-trivial rank for this spectral density. Is the point. Again, I don't have a lot of time. That's stuck on the motivation, but here the bottom line is that we derive all this. What it all comes down to is to this rank of a matrix that we get by stacking the y's and the x's together, right? So this is the rank M. And long story short, again, they're not hard derivations. They're in the paper. Is that all these parameters, the size and the lambdas, they're actually just deterministic functions of can be reduced to being deterministic functions of a matrix delta, orthonormal matrix delta, n plus k minus m by n minus r. And so basically, if you plug that in, we can construct. So we do that to get rid of this constraint that's explicit in the density with respect to this Lebesgue measure. We obtain now a density that's essentially this p subscript eta towards the bottom, which is a representation in terms of just the parameters. So we got the lag length p, the rank r, and these deltas, which is all we need.
I think we need to wrap it up, and then we can actually discuss the rest. And
okay.
After. where do I go?
So quick. Okay. So yeah, the point is that
where do you want me to land?
Let's just go back one step to this Monte Carlo, and I'll show the punchline. So we get a, yeah, here, right? So again, in the paper, you get a nice Hamiltonian Monte Carlo is the machinery for the MCMC. There are just a few tweaks that already exist in the literature in order to implement this. It works quite well on even with large data. So I mean, this approach will work best with when you consider, again, like large data, right? So, or larger cross sections. So in this case, so what we do here is this Monte Carlo exercise, among others, where we take a multi-sector DSG model. The multi-sector DSG model has 101 states and 33 shocks. So 3 of them are macro shocks, 30 of them are sector-specific shocks. Anyway, one of them is a monetary policy shock. So generate data from this DSG and, you know, just compare, first of all, what we get in terms of these impulse response functions to this monetary policy shock. So the key thing, I guess, to look at is the response of, let's say, output and money growth. Again, we take various data set lengths, so either 220 observations or 120 observations, and we just compare the singular VAR approach to, you know, a standard Bayesian VAR approach. And just to show the fact that it's not the shrinkage restrictions, not the, you know, Minnesota type priors or whatever that actually, you know, get us to the better inference. It is in fact the fact that we can estimate this singularity that's we got information about in the data. So if you look at this money growth, let's say response, well, you know, you notice that the standard Bayesian VAR actually does quite poorly in estimating the response at the shorter horizons. It estimates a negative response to expansionary monetary policy shock. And the other thing to note here is that as we increase the data size from 120 to 220, the Bayesian VAR actually does kind of worse from that. Whereas, like, yeah, imposing this singularity, again, because of the matching, improves the ability to recover this true structural shock.
I don't understand what you mean, but you're using the word matching in various ways. Some minutes ago, it meant to be identification. Now, these are impulse responses. Okay, now the model, you could just take Leaper's model and numbers he gets for his parameters, and then you do these impulse responses, fine.
Yeah.
But I'm not, one thing I don't understand is, you know, one does better than the other. I mean, in what sense? Are you talking about fit of data? I don't see anything here that tells you about fit of data. That's what I don't understand. What do you mean better or worse? Or you mean this model is the truth? And explain, please.
Okay, so the red line in each of these plots is the true impulse response function from the theoretical model that's with some values of the parameters chosen, right? So you assume that theoretical calibrated theoretical model is the data generating process. So you generate 500.
Okay, so the red line is the assumed truth. Okay.
The assumed truth, right? The black lines are the 68% the highest posterior density limit points for the intervals, right?
Okay.
So if you're looking closely, there's also a gray region. That's the variation across the data sets that get estimated. So for example, when you look at the BVAR with the 220 observations and the response of money growth to a monetary policy shock, yeah, that one, you see that clearly a monetary policy shock leads to money growth, positive money growth that stays positive for a long time. If you apply the standard BVAR with the shrinkage priors and all that, we actually estimate that a positive monetary policy shock leads to, our inference would be that it leads to a negative money growth initially, right? So we've got the entire HPD interval across all these 500 data sets being strictly below 0.
Okay, I think now I understand that. So you have one set of graphs and numbers generated by the assumed truth, and that gives you a bunch of the simulated data. And then to that data, repeatedly, you apply your method versus BVAR.
Yeah.
In a sense, you've got three things are graphed. The
Yes.
truth, yours, Vivo.
Yeah.
Okay. Okay, now I understand.
Yeah.
Okay.
Majid, if you agree, I'm going to stop the recording here, and then
Yes.
we can open, we can follow up on this
No,
point. And
maybe just let Eric conclude real quick, and then we stop recording.
Yes.
Just
So
the punchline.
So the punchline is you know that practically it works quite well, even though it's like using Monte Carlo on systems with like really large dimensional parameters. That's really the only big hurdle here, but it does work quite well. And the punchline is that imposing this or allowing for this the data to provide us inference on the singularity or on the rank of the spectral density does seem to improve our inference on things like impulse response functions if we're trying to get structural inference from observed say macro data.
Stop the record.